I'm going to be discussing propellant-less propulsion from using conformal gravitation. I'm going to start discussing what is the M field, which is what makes this different than Einstein's general relativity. Then I'm going to discuss, up to here is going to be the Hohenlohe-Likar. This is going to be a formulation that I have in order to address Jim's formulation. I'm going to discuss waves in a weak gravitational field and comparison with astronomical observations. So we start with Einstein's general relativity, like Lance very well said. That should be our point of departure. So Einstein's general relativity can be said that is relating the geometry of space-time, that means the curvature of space-time, which appears on the left-hand side of the equation, to matter energy that appears on the right-hand side of the equation, and K is a coupling constant. And here you have the membrane analogy that you may be familiar with, that really gravity is not a force, but is actually bodies going in what in curved space-time turns out to be the straightest line, which is the geodesic motion. So they are just doing what naturally has to happen, and it's all due to the deformation of space-time. The more mass you have, the more deformation of space-time you have. The less mass you have, the less deformation of space-time you have. This is the so-called metric, and it's real. You can think of this as you just see it like Euclidean geometry, where you know that if you have a triangle, you have a description in terms of the sides, or think of this also as if it would be a Euclidean geometry. This metric is just a matrix where you have in the diagonal ones, and off diagonal you have zeros. And then to describe a complex manifold, that means where space-time is deformed and is not Euclidean, then these things turn out to be parameters that, like for example, Lance showed, they are not even constant, but for example, you were showing the Kerr metric where you had a number of parameters there. So, these two guys have been mentioned before, Hohenlohe-Likar. Actually, what they did is, again, we have here the Einstein's description of the geometry of space-time. The curvature of space-time is exactly the same. And on the right-hand side, you have the stress-energy momentum tensor. It's exactly the same. The only thing is that he has this extra field, M as in Mary. It does not stand for your mother-in-law, but I'm going to describe what it stands for in 1 minute. And it appears both on the left-hand side of the equation, the part that describes the geometry of a space-time, as well as appearing on the right-hand side of the equation. And on the right-hand side of the equation, it appears in a nonlinear form. And this is the scalar field. So what is this M? This M is what the difference between their theory and Einstein's theory. It's a scalar field. It's a scalar. It is not a vector. It is not a tensor. It is a function of space-time. That means that it's a function of time, and it's a function of location in space. It's a field that endows particles with inertial mass. In their view of the universe, you have these particles that have no mass unless they are coupled to this field, and this field is what gives them the inertial mass. And this inertial mass is given mainly through non-local interaction between these particles and the particle itself, that is Mach's principle, and also through self-interaction. This field results from a continuum approximation of a separate theory they have, where they have discrete fields that are coupling a particle one-to-one. So I have, for example, the device that Martin is testing, and you can couple it to the moon, you can couple it to Sun, to the Jupiter, to the star Alpha Centauri. All those couplings are discrete couplings. When you sum them up and you describe this as a continuum, just like, for example, when you have a fluid which is made out of molecules, you have a continuum approximation, or for example, you have a solid too, you can do a continuum approximation of these separate fields, and this is what this M is.
What happens when you're using Holman transforms?
When you what?
Holman transform trajectories.
I'm sorry?
Holman trajectories.
That has to do with that had to do with motion, and I'm going to have a slide, so let me address that later. So it results from a continuum approximation. Well, I said that already. It is not a mass. It is mediated by massless particles. They're called dilatons. It doesn't have any mass. It's massless. It has units of the square root of mass density divided by curvature. Why? Because I'm going to show you, it appears in the coupling constant. It has features both of geometry and it has features of mass. And it has to do that in order to confer inertia to the particles, because space-time, the curvature of space-time, it affects this field, and that's part of conferring these properties of inertia, and that's how this effect is going to appear. It couples space-time geometry to the energy mass source. Now, conformal. What is conformal? Conformal is something that we are all very familiar with since we are kids. We live in a round world, we know that. But when we have to look at a map, it's flat. So how am I going to represent the world on a flat surface? If my world is a small town and it's practically flat, it's not a major problem. But if I know that there is Europe, and there is Atlantic Ocean, and then there's America, and there is a North Pole and the South Pole, then you have a problem. This is called a conformal transformation. It's actually a mapping of one surface into another. So for example, for a mapping here, we are going to map the surface of the Earth onto a flat surface. Now, a conformal projection, and I just took this out of the internet in order to save time, start by saying the preserved shape. No, it does not preserve shape at all. Only if you are in an extremely small part that you can say is almost flat, it will preserve the shape. But in general, you're doing this because you're dealing with something that is not flat. So you have to say it outright. It does not preserve shape. It does not preserve area. It does not preserve volume. The only thing it preserves are angles. This is clear here. Take a look here at this projection here. It's called the Lambert conformal conic projection. Well, you're going to say in this projection, Greenland is kind of reasonable. But as you get here to the Antarctica, that's not reasonable. That's not what the Antarctica looks. It's extremely distorted. So is distorted this country here that I know well called Argentina. It's not that long. So it does not preserve volume, area, length, or any of these things. It's not a volume preservation transformation. The only thing that it preserves are angles. It has nothing to do with a rest frame. Rest frames have to do with velocities. But this is something that has to do with a transformation that preserves angles. It does not preserve anything to do with length. It's something that we aeronautical engineers are familiar with. When we study aerodynamics, we are familiar, for example, in when aerodynamics looking at the conformal mapping, is called the Joukowsky transformation of a rotating cylinder into an airfoil. That's how we won World War II. This led to a number of greatly designed airfoils that Langley had. When somebody says that a conformal theory reduces to Einstein's general relativity, no. If you have an airfoil that was studied with a conformal transformation, the airfoil is not at all a rotating cylinder. The transformation is a mathematical device in order to be able to preserve angles, but you have to clearly separate the two things. This is not equal to this. So only angles and ratios are preserved, length, area, and volume are not preserved. Geodesic motion is not preserved. Since geodesic motion is not preserved, Mr. Paul Murat, what you were asking me about the trajectories, I'm telling you that even the geodesic motion is not preserved. So the orbital transfer you're talking about is also different. In one, think of this again as you moving on the surface of the actual Earth, which is curved, and somebody telling you, now from now on, you're going to be on this flat surface. Your movement is going to be different. Your path is going to be different. Your velocity is going to be different. You have to clearly separate the two universes.
The question is that I asked some people how to use a field of equations into trajectories. And very few people started coming up with the geodesic equations. And then if you start looking at it, you talk about it in terms of orbits, and the answer to that question is yes.
So the equation of motion for gravitation is no longer a geodesic in this conformal transformation. And this is something that I didn't invent. Holland and Licker, in their very first paper, they say that the equation of motion does not satisfy a geodesic. Which the inventors of this theory, Hoyle and Licker. So did Branson Dickey. They all accept, as soon as you put that M field and you are in that field, it does not satisfy the geodesic motion anymore. Now, let's consider, again, this is the so-called metric that I told you that describes the curvature of space. In Euclidean geometry, is like a lot of ones. And in a curved surface, they are not ones, they are different values, and maybe a function of time. And do a transformation where you have an omega, which you can say is omega squared, relating a new metric to the old one. This is the conformal transformation. Now, you can take, very interestingly, that M field I showed you. You can take a constant M field. That means what does a constant mean? It's not a function of time, not a function of space, it's a constant. It's the same here as there. It's the same near a black hole as the one that is in space between the stars. That's a constant. And you have that in the denominator, and in the numerator you have the actual M field, which is a function of time, of space. It's a function of gravitation, etc. And you do this transformation. When you do this transformation, you get Einstein's general relativity. That does not mean that these theories are Einstein's general relativity. That means that all you did was to take the M field that was in the field equation and you put it into the metric. So you hid it there, but it's still there. So now you have a different metric. So it has a star because it looks like Einstein's general relativity, but it's not, because now the metric has the M field there. So it is like your real world, which is the Earth, and then the conformed mapping, which is a flat surface. They are different. Or like your airfoil, which is, on one hand you have the cylinder, and the other one you have the actual airfoil. They are different. You can make them look like each other, but they are not. Now, the reason, this is a very interesting property, And after Horler-Likar, that was one of the few, the first one to do it. Actually, Dickey did it first. There have been a number of them, and it's using a string theory and so on. So actually, I would say most of the gravitation theory is being studied now at Stanford, MIT, Harvard, and so on. Many of them are conformal gravitational theories because they have very, very interesting properties. Now, the field equation, which I showed you, there was a tensor there, and Lance was talking, well, there are 16 equations, but there are 10 independent. Actually, for many problems, they can be reduced just to one equation in terms of scalars, which is an invariant. Because when you have a gravitational field that is centrosymmetric, that means you have a spherical mass, for example, then it turns out that you don't have shear, you don't have vorticity, you don't have off-diagonal terms, and for many problems, all you have are diagonal terms that it can be all most of the function can be expressed in terms of the invariant equation. So in order to understand what's going on, it's a good idea to take a look at this equation because, like we said, we depart from general relativity, from what we know to what we don't know, to understand what's going on. So in general relativity, we're going to have the scalar for the curvature, it's called the Ricci scalar, the scalar for the stress energy momentum tensor, and then we're going to have the coupling constant. And the coupling constant in general relativity is 8 pi g divided by c squared if you have t in terms of mass density, like I will, or it's over c to the fourth power if it is the energy density, like Lance was using. And you have this extra term that all those nonlinear terms that were very complicated, they exactly, this is not an approximation, they exactly reduce to the, if you want to call it a 4 Laplacian, or if you want to call it a D'Alembertian, this rectangle means that you have the second derivative with respect to time divided by c squared, plus the second derivative with respect to x, plus the second derivative with respect to y, and so on. That's what that term means. And it's all divided by m. Now, there's another interesting equation that Horner-Likar had that relates this property of the M field that confers inertia to the particles. So this is a stress energy momentum tensor, which is, in the simplest approximation, could be just like the mass density. So you have the mass density here. And this is the number density of particles. That means the number of particles, not the mass. They don't have any mass. That's the number of them. And what gives it the mass is this M field. This is their equation. So if you plug that here, then this equation becomes this, which is, you have the M field and then the number density of particles. And if there are no particles and it is 0, then all you have is the M field. So like it's in space-time, you have just this M field. This is a so-called Klein-Gordon equation where this can be shown to give rise to these particles called dilatons that carry this inertial field. And they are just a function of the space-time geometry, this R.
Why does Klein from Schrodinger's way of equation?
Klein-Gordon equations in general are equations that where you have the D'Alembertian of something plus another function times that function that you are differentiating on equals 0, and you can use quantization in order to get particles out of that.
All right, so the box that you're showing me is a wave equation, right?
You can view this as from a quantum point of view in order to say, okay, there are particles coming out of that, if you want. Okay, so if you look at the situation for a constant m field in time and space, the case I discussed, then this is, which is called a Dahl inversion, which means taking the second derivative with respect to time, the second derivative with respect to time is 0, and then one gets Einstein's field equations, because this term here becomes 0, and then you get that. This gives you an explicit formula to relate this constant to the coupling constant of Einstein, because you have the same equation and you have this coupling here. So that means that 6 divided by the square of the constant m field is equal to 8 pi times the gravitational constant divided by the speed of light squared.
Jose, I'm confused. If you look at that equation, m0 is a constant. And then you're having this square operating on m0 to end up with a Laplacian equation or a wave equation. Isn't m0 a constant? If it is, then all the other terms go to 0.
This is what I'm saying here.
Yeah.
Yes.
Okay. Thank you.
This went to 0. Therefore, all you have is this.
No. If you look at m0 though, you're picking m0 as a constant.
No. I'm taking m equal to m0 as a constant.
Yeah, but I look at four lines down there. You got 6 m0 squared.
No, look. Put m equal to m0 here. You get 6 divided by m0 squared.
Okay.
Plus minus 6, the derivative of m0, which is 0. Therefore, you get r equal to 6 over m0 squared times t. That's what I have there. So then, we know that this is the case. Therefore, you know that m0 squared has units of mass density divided by curvature, which is the units of mass per unit length, the square root of mass per unit length, and therefore that the constant m field is given by the speed of light and the gravitational constant. So for a constant m field, it's just a function of the speed of light and the gravitational constant. So far, I didn't invent this. This is all in Horner-Licker, and it's all in Brans-Dicke. However, it turns out mathematically there's a number of theories that are mathematically similar. Brans-Dicke's theory, Horner-Licker theory, and a theory of Dicke where he has the speed of light as a scalar field that is the one that is not constant but is dependent. And actually Harrison, in a book in cosmology in 1981, described this very interesting. He says, all these theories have, although physically motivations are different, they have equations that look very similar, and actually you can convert one from the other by transforming this thing. Why is this? So he says, this is like a machine, which we call a new universes for all, where you have conformal transformations. So you take the one universe, and universes come out, and you have here a dial. So you may want to have the gravitational constant to be a function of space and time. So you dial that one. Or you want to have the speed of light a variable. So you change that one. Or you may want to have the m field, which is related to the inertial mass, as a variable, and you dial that gauge. So when you look at it, they're all conformal theories, and you can relate one to the other. Just a minute, John. And this is all due that they are all having scalars that are coupling the geometry of space-time to the mass density. And in that coupling constant, all you have are these scalars. The speed of light, the gravitational constant, and the mass by doing a transformation, the inertial mass. Yes, John?
I just wanted to comment that there's quite a bit of freedom you now have to choose a universe.
Yes, actually he says that.
That may have no resemblance to our own.
So actually he says that, physicists are then very unlikely to start playing with all the gauges at once, because then you have a real mess. So they all play with one gauge. So Brans-Dickey chose the G dial, and Goldner-Likar chose the M dial. And somebody may say, no, I'm going to consider the speed of light on my variable. I may play with that dial. But from a mathematical point of view, you can relate them to each other. It's just a physical interpretation of it. And then you have to go to experiment and see what's going on. Is G a variable and so on? And I'm going to go over that next.
We can assume that the inverse transform is unique.
The inverse transform of what?
That box. Can I go back the other way in a unique fashion?
No. No, because they are nonlinear. First of all, they are nonlinear partial differential equations. Therefore, it's the inverse transform and not.
The conformality can go only one direction, but not the other.
Well, okay. If in the cases I showed, which are the simple case where you have only one variable that you are dialing, I can see that there may be an inverse. It seems to me that if you're playing with all the variables at once and you have a nonlinear theory, I will not be surprised that there is not an inverse.
Okay.
And even
you answered by simply saying if it's nonlinear,
yes.
That answers the question. Thank you.
So now, so then it occurs to me, basically we know that the constant case is a trivial case of Einstein. The gravitational constant is a constant throughout the universe, it's a constant. So and we know that this series, a scalar tensor series, where originally they thought there was going to be a lot of variability, they were falsified as far as how much variability there was, little by little. So in the 1960s, they started doing experiments to see whether the gravitational constant was not a constant, and then they determined, well, it is a constant, at least within these parameters. And since then, we have been doing more and more experiments. So we know for a fact that there is a big, if either is completely constant to all levels, or is constant to some range, and then there may be a small part of it which is time dependent. So I said, well, let's then decompose the field into a constant term plus a time dependent term. And I know from experiments already that this time dependent term is going to be small. How do I know that? Because there's a lot of experiments showing that time dependence has been ruled out to be quite small already. So let's do that. And therefore, let's carry this through the equations, and then we get that we can express the equations in terms, either in terms of the M field, or we can express it in terms of the M field in the derivatives, but the gravitational constant, since that's the one you know, you may want to keep it here, or you may want to express it completely in terms of the gravitational constant, which is not a constant. No, G naught is a constant, but in this case, GS will be time dependent. That will be a very small part of it that is time dependent. Now, we heard today from Lance again that Ciuffellini and Wheeler said that mass energy there rules inertia here. Mass there rules inertia here. Mass there rules the inertia of your little device. If you go to the potential phi in Siama, then you have the G, and you have the mass of the universe, not your mass of your device, and the radius of the universe. It is all that mass there that rules the inertia here. The mass of the universe is 10 to the 53 kilograms. The mass of your device is only 0.2 kilograms. If you were to do this inertial induction, and you want to get a big effect, you're going to have to oscillate with respect to time all the mass there, or a lot of it, 10 to the 53 kilograms at the appropriate frequency. I think that's very unlikely, or practically impossible. And also out of luck, it's extremely unlikely that all these things are going to be vibrating there in unison, in synchronous fashion. So you have to resign yourself to that. The only thing that you are vibrating is this, and when you say that mass energy there rules inertia here, that's already in conflict with the concept of by doing something to here, you're going to change the inertia, because you just said that the inertia is due to all the stuff up there. So the conclusion is that the time-dependent component must be significantly smaller than the constant component to be consistent with experimental data, and that it has to be mainly associated with self-interaction, because if there's any hope for this to work, and you having to vibrate something locally, and that affects its own inertial mass, you're saying that there's a self-interaction, because you're not vibrating all those guys out there, you're just vibrating this one. So this, a very small component, has to be due to self-interaction. So how much time do we have?
You've got plenty of time.
How much? Okay. Okay, half an hour. So if we substitute this term in those equations that I was discussing with Paul, and we do this term by term, we see what's happening, because this time-dependent term is very small, and I already showed you that if it is 0, then you have this equation that gives rise to dilatons, because all you have is the ms, and you have any m naught here. And then if ms is 0, then you have Einstein's. So actually you get a decoupling of this equation by assuming that you have a very small time-dependent term and a constant term. This mainly Einstein equation, and then you have the separate one. And the hope is that there is something in between, but it's a very weak coupling. And that's what is in scalar tensor theory. We all talk, that the experiments are showing very weak coupling. Now, can this be viewed as a source? Yes. Actually, when you plug the equations and you have the T, the stress energy momentum tensor, is the mass density, and you know that there is a pressure component. This appears also in Einstein's theory. And then you have this term I was talking about that has the time-dependent M field, right? And I can call all this, like Jim did, a density. Why not? I mean, just give it a name. You call it Jose, or you call it Heidi. I call that rho field. It has the units of a density. It's not a density, but it has the units of it. And therefore, that is the second derivative with respect to time of this M field. It's not the second derivative with respect to time of your mass. It's also M field. And Martin had a question last year. He says, Jose, well then, how is this going to work? Because what I'm vibrating is my mass density. I don't know what the M field is. How am I going to get there? But I'm showing you that if you want, it can be viewed as a source, which is actually the point of view that Jim takes. But there is a dual interpretation of this any scalar coupling field. This is not the only field, and there's a field that is not being denied, I think, by most people nowadays. You heard about dark energy. Most people think that experimental evidence is consistent with dark energy or the so-called cosmological constant. Einstein himself had a cosmological constant. He had it, he took it out, and then he said it was a big mistake to have taken it out. It's a scalar. Where did Einstein put the cosmological constant? He put it on the left side as a scalar with a geometry. What is the present point of view? The present point of view of this is as dark energy, which is a fluid that is actually exerting pressure in the space-time, pushing things away. So we are familiar that the cosmological constant itself can be viewed either as space-time geometry, or it can be viewed as a source. You can do both. And the present point of view is to look at it as a source. And we can also do that with the M field. We can look at it as a source. Both views are perfectly compatible. When we put the cosmological constant on the right-hand side, it turns out to appear here, and it has the same prefactor as the derivative with respect to time of the M field, or like it appears also in Jim's equation, c squared divided by 4 pi divided by g. You are free to look at it as a source if you want. You are free to look at it as due to geometry. And the reason is because it's a coupling field that has to do with both. And these guys look at it as being a scalar field. But now we're going to take a look at answering Martin's questions from last year. Jose, okay, you have all this thing that you're saying the M field is not really the mass density. So how is this going to make sense now? Because what I'm vibrating and what I'm changing, hopefully, is the mass density. You can do this by taking a look at the equations. This equation appears in Horner-Lickar, which is the stress energy tensor, which remember, which look at, think of this as being the mass density, is equal to the M field that will give the inertia to the particle. Heidi is a particle that has no inertia, and I am the M field, and I'm going to shake her hand, I'm going to couple with her. When somebody else, now I gave her inertia. Now, so let's take the derivative of this equation. And this funny rectangle I have there is just a double derivative. Think of it as just, it's the double derivative with respect to time, but the derivative with respect to space, and so on. This is a way. So let's think of this as the derivative. So the derivative of t is equal to the derivative of this product. And you know from differential calculus, therefore, is equal to n times the derivative of m plus m times the derivative of n. Now, if you want, you can put also the density here and just substitute there. And then you can divide this by the equation itself, and you end up with this equation. Now, if you want, you can end up here. And you already see the coupling here, because what Jim has is the double derivative with respect to time of the mass density, and that is related to the double derivative with respect to time of the M field. So you can substitute that. Now, for simplicity purposes, you can say, let's say I'm going to keep the number of particles in whatever I'm doing constant, and I'm going to be changing the mass density otherwise, but I'm going to keep the number of particles constant. Then that is equal to 0. And let's say also that the pressure is much smaller than the mass density when you divide it by the square of the speed of light, which is usually the case. And then you end up with this simple equation, which is that the double derivative with respect to time of the M field is equal to the double derivative with respect to time of the density. And you can do that substitution, but only as an interface condition. What this means is I am Jim. I have this idea, okay, I'm going to be vibrating this thing, and so I'm going to have now hopefully a change with respect to time of the mass density. So it's doing that, and because what I'm doing is already coupled with the M field to the rest of the universe, and remember I'm here and so on, and now Heidi is going to start shaking me here, so I'm shaking here. So now I'm going to start shaking something else. So this is this interface condition here, where here you have Jim's term, and then is transmitting this all the way to with the M field to all the particles that are being connected to it. And that's a connection, and then if you do that, you end up with Jim's equation. Now, let's look at the case of weak gravitational fields, which Lance, yes?
Sorry, question going back one slide to where you say this leads to Jim's equations.
Yes.
I see how you're incorporating the energy fluctuation. Does this deal at all with the proper acceleration that has been posited as required for this?
No. So I look at this, I like to do this completely from general relativity. So my derivation would be that to predict the motion, I'm using general relativity. And so how does general relativity deal with the motion of a particle? With the equation of motion. That's where the geodesic comes from. So I'm not going to do this thing of taking the density and then having a simple model and all that. Like, no, I have the equation of motion, I have a geodesic, solve that and see what that gets you. So now let's look at the case. All that I did is amazing. It's fully nonlinear. Okay, Lance is fully nonlinear. It's beautiful. It's only now that you are going to introduce the infinitesimal perturbation to look at weak gravitational field. But those equations I gave previously are nonlinear, and actually the M field for the invariant equation, also nonlinear terms, disappear. And it's fully general for any space-time geometry. Now, John, when one does this, at this point, which is what Lance was doing, waves in a weak gravitational field, that means that black holes are out. Because black holes are the strongest gravitational field you can find. So whenever somebody starts talking about this and starts talking about H, they already said no black holes. Do you agree?
No, I do agree.
Okay, good. So
You compensate for it so that you can deal with, let's say, waves in strong gravitational fields. How would that change that methodology?
yeah, well, you know, it's like a baby. First you have to start walking, and then so you're telling, yes. So let me deal with the waves in the weak gravitational field to see whether we understand something before we start talking about. But at the moment, Jim, as far as I know, has not been dealing with any black holes. What he has been dealing with is just normal matter with PCT crystals and so on.
You could be lying.
So that sounds very esoteric to me to start talking about black holes. Nor I know of any that is in the close vicinity of us. So this is just a metric perturbation where the mixed components are much smaller than 1. It's extreme, by much smaller than 1, I mean like 10 to the minus 21, extremely small. And like Lance was saying, you can use the harmonic gauge, or you should use the harmonic gauge in order to be able to solve the equations because of the reasons that he gave, because otherwise you have too much freedom. This is nice because it has the property of zero divergence. So that allows me then to simplify this to this equation, and then I can replace the H perturbation, which appears here, by the potential, and then assuming that you have a case where the pressure term is much smaller than the mass density term, you end up with this. And what do you have here? On the left-hand side, you have the inversion of the potential, and here you have the mass density, and here now you have this term. We have the time derivative of the part of the M field which is time dependent, which we said it was very, very small because it's a self-effect, because you're not vibrating all that mass out there that is responsible for the inertia here. You're just vibrating this thing. So I expect it to be very small. And at one point I said, well, how small? Because this guy is also very small. The cosmological constant is very small. And then actually you can use this equation to see actually, according to Jim's experiments, they're very interesting because what he's showing is, okay, he's getting a small effect, but it's still orders of magnitude bigger than the dark energy. So it's a very interesting thing. So, you know, people are studying dark energy, and if this thing is real, it's small, but it's still much larger than anything that has to do with dark energy. So, like Lance was saying, we have to depart from what is accepted and known general relativity. We did that. We added the M field. Now we have to take a look at measurements. Yes?
On that previous equation, on my talk, I just showed that getting away from nature of the time component is an illusion of the gauge. So, what say you? This is a choice. You're seeing this wave behavior because of your choice of gauge. And as I showed, it's
There's more than
not
that.
real. There's no radiative wave dependence on this component of the potential.
Well,
So,
yes, I got you. Let me answer, first of all.
bringing it on you, but
No, I like it. It's very good. Okay, first of all, you say there is non-radiative effect. Now, from a general relativity point of view, you know that in order to have radiative effect, you have to have the minimum of a quadrupole. And Jim has a quadrupole. So there are radiative effects.
I'm just talking about the field.
I'm talking about his experiment. In his experiment, he has a...
Talk about your derivation of this equation.
Yes.
And previously I showed that the time component, the time doesn't obey a wave equation. It obeys Poisson's equation. In
No.
reality, the true gravitational field, this is an artifact of...
No, because I didn't go through inertial induction. This derivation has nothing to do with the induction and derivation that you were doing. This derivation is straight from scalar tensor theory, taking into account all the terms. This has nothing to do with it has nothing to do with Maxwell's equation. There's nothing about Maxwell that I use here.
You're saying if general relativity, your choice of the gauge is giving you an illusory, there's no wave.
It's not illusory when I have a binary system and they are rotating and it emits a gravitational wave. There's nothing illusory about
Those
that.
gravitational waves are in the space-based components of the metric, not the time component.
And I didn't say they are in the time component. Actually, if you look at this, as I said, this is a self-interaction effect. Therefore, if it would be a time-dependent effect, then when you take a look at Jim's equation, you will see in many ones I see that it's only the time component and not the derivative with respect to space. I think that because, correct me if I'm wrong, Jim, what Jim said, okay, if you look at the distance between what you're vibrating and the mass out there that is responsible for the inertia is many times larger, something like 10 to the 20 times or more than the zone where the space-dependent terms are important. The same thing as in gravitational waves. So therefore, you can do that. But when you take a look at that this is a self-interaction effect, if it is a self-interaction effect, then actually when you solve the equation, you're going to see that the derivative with respect to space are going to be most important. And I have them here. They're here. I didn't take them out. They're here. And actually, see what's happened, again...
That's the new stuff you put in, everything on that second row. But the top row is just standard general relativity.
No, this is just a perturbation. If you take a perturbation, you get this.
I don't want to derail your presentation.
You get both. And it turns out that the derivative with respect to space are going to be extremely important for a self-interaction space.
You have to worry about the gauge. That's what I'm saying. You can choose a gauge and see whatever you want, but...
You don't have to worry about it when you specify what it is.
This is non-standard parallel relativity. He's talking about a scalar tensor
Right.
that's beyond.
Could you say anything about the metric? Are you using a standard metric for this definition?
Yes.
Yes, dx squared plus dy squared.
This is a standard metric. The M field is exposed. I don't like this when people say that, oh, I can make it look like general relativity because they are hiding the scalar field and therefore they're playing with it. But anyway, let's go back to the experiment. It is a quadrupole. He has a bigger mass. Then he has the piezoelectric electrostatic rod, and then he has a smaller mass. And if you look at it, that is a quadrupole. And actually, if you look at, then you have the acoustic equations that are going to give you your change with mass. And actually, you're going to see those waves, which are real waves. Nobody's going to dispute the acoustic waves that are going to give you the change eventually the change in mass, have a well-known distribution with respect to space and with respect to time. And therefore, this term here is the one that becomes very important in this formulation. So let's take a look at the astronomical data. How much time do I have?
Less than 10 minutes.
7 minutes, okay. So the problem with astronomical data, when people tell you, oh, Jose, a scalar tensor theory was falsified. No, it was not. What was falsified was strong coupling of the scalar field. The question is the coupling zero or is a very weak coupling? And that is what is being studied. And scalar tensor theory is being used on all major universities. There's nothing controversial about it. This the inflaton that describes inflation is a scalar field. Dark energy is a scalar field. There's anything nowadays in physics it deals with scalar fields. There's nothing controversial about it. So another question.
Any physics or experiment at the frequencies that you're working at, like
So actually that's the problem that when we look at the coupling of the scalar field, everything that one looks at is very slow. If we look at the moon and the planets, they are moving very slowly. The frequencies are extremely slow. Now, one of the most recent papers by José and Malek from 2004, and they used this pulsating white dwarf, which is considered by many to be the most accurate clock in the universe. And it is a natural clock, which is extremely accurate, and it's due to the pulsations. And these are gravity waves. They are not gravitational waves, they are gravity waves. They are gravity waves due to the fact that the white dwarf is a fluid, right? And therefore you have an equation that relates pressure to density, and therefore you have buoyancy, and you have gravitation. And the interaction between buoyancy and gravitation gives you waves that are well known even in our atmosphere. Those are called gravity waves, and it turns out that 40 stars are very, very periodic and very accurate, and it is much faster from the point of view of frequency than when people take a look at the coupling of scalar theories by looking at the planets or something like that. That is what was being done by Dickey. But still, this frequency, although it's much faster, it's about the period of 215 seconds. The period of 215 seconds is much faster than what it takes for any planet to go around the sun. Still, it's 7.5 million times slower than the experiments that are being done by Jim. And the experiments that are being done by Jim, they're not only at a much higher frequency, but when you look at the theory, it turns out that the effect goes like the frequency to the cube, maybe to a frequency to the 6th power. So there's this turns out to be a huge thing. So when they say that they constrain the change of the gravitational constant with respect to time divided by the gravitational constant to be much smaller than 10 to the minus 17, 1 over second, this is an extremely slow frequency. You can do this. You can put this in terms of m, the m field, if you want, or if you like to play with variable speed of light, you could do that too. In any case, one can posit, and I would like to posit, it is possible that that there is a time-dependent term that is very small because it's due to self-interaction, and that you have not observed it in astronomical observations. Why? Because they're extremely slow. And that goes also for binary stars. They're extremely slow. And it also that goes for pulsars. We have looked at that. A member of our team is Marshall Eubanks, which unfortunately is not here, but he's a cosmologist. He has been involved actually even with Shapiro in the initial experiments to look at these issues. So, and if you're interested how they derive this constraint, actually I wanted to show that because this is very interesting. This is in the paper by José and Malek, and how they derive the constraint on the scalar tensor theory is by doing the same kind of differentiation I was showing you, where you just take the time derivative with respect to g here, and then you get this extra term here. And then you say, okay, now how big that is. That's exactly how, and that is in their paper. So, having said that, and before I say goodbye, I have only 2 more minutes, I'd like to show a prediction that I had made the last time we had a presentation, which was at Aerospace Corporation last year. You know that in Jim's experiments, he has a big mass, which is the brass mass, and he calls it, I think it's something to rely on. It's my rock of Gibraltar.
Reaction mass.
And you have a reaction mass. Then you have the piezoelectric electrostatic rod, and then you have nothing, or you have some small plate there in order to compress it. But in my solution, which is numerical and it takes many hours to run, I tried, what happens if I change the masses of both things? If I have them equal and symmetric, I don't have a quadrupole anymore, I have a dipole and I get 0. No thrust. But it was very interesting, as I showed you last year, that I predict that actually, if I plot the thrust force in micronewtons here, and here I have a log scale of the brass mass, and I keep my aluminum mass constant, that's very tiny. Although you do have a behavior like they are finding in their experiment, where there seems to be an optimal mass that is close to 0.1, and I can predict that, I have this behavior here that if I have a very much smaller mass, which is just enough to give you an asymmetry, but it's quite small, I have practically the same effect. And now I'm interested in doing an experiment on that, because if the experiment shows that, I say, well, that's interesting, it agrees with this. And there's another reason, that if we are going to be making nano devices, I don't want to have, and I don't conceive of having a huge brass mass or another big brass mass there. I like to make nano devices which are as small as possible, instead of having something very big there. And Heidi did this experiment, and putting an aluminum mass instead of a brass mass, and the aluminum mass is the same mass as the one at the other end, and then you are going to ask me, where is the asymmetry coming from? The asymmetry is because I'm taking into account the rubber pad gaskets, and I'm taking into account also the holder. And that is also attached there. So you already have that mass to rely on. And actually, the thrust was very similar. So we have an experimental point here, we have an experimental point here. When you reduce it, then the thrust became very small and it disappeared. So we have a few experimental points, and they are quite promising. So in conclusion, the inertia here is mainly due to the mass there. That's what Ciuffolini and Wheeler told us. But we're only fluctuating the mass here, not the mass there. And it's going to be impossible in my lifetime to be able to fluctuate all the mass out there. So conformal gravitational theory is consistent with experimental data if one decomposes the M field into a constant and a time-dependent component. And I know that that time-dependent component has to be very small, because there's already a lot of experiments that have shown that, and that has to be explainable by self-interaction. Thank you.